Great to have Mateusz Michalek, and he'll be speaking towards generalized Schubert varieties and Anabelian Matroids.
Thank you a lot. It's a great pleasure and honor to be here. While preparing this talk, I realized that out of all those words, I can only focus on 2 words. This is based on a joint work with a few people, from those who are here, Rodika and Leonid. But I would like to focus a lot on results with Julian Weigert and Gaku Liu, quite recent. And probably I will not have a lot of time to say, but there is a forthcoming work with Otong. Now, there are a lot of names here. It's not like one article, but one should not be scared. That's why we now branded it Boden the program. There are many people working on, but also many places, new questions for you to join it. I know there was no coffee in the morning, so don't worry, there will be no math talk. Instead, I decided to tell you a fairy tale. And when it comes to fairy tales, they are not supposed to unnerve you or be offensive. They are just supposed to be enjoyed. So please sit and hopefully enjoy. It will be a fairy tale over complex numbers for simplicity. But we should start with imagining a wizard who sets up on a quest. And it's a hard, dangerous quest of inverting diagonal matrices. Okay? So the wizard sets up on a quest. We want to invert Dn will be n by n diagonal matrices. And immediately, as the quest starts, the wizard runs into a first obstacle. You may think it's easy, but once you will encounter a diagonal matrix like this, you will not be able to invert it. And the problem is essentially as bad as it could be, because such things form a codimension 1 obstacle. Okay? So the wizard uses the first spell. It's called projectivization. And there is a theorem that if you were going to a projective space, such a thing should not happen. That is, if you have a map not defined everywhere from a normal variety, there is no chance that in codimension 1 you will have problems. So let's try to work up to scaling. We make our spell 1 projectivization. That is, we pass from the affine space to projective space of diagonal matrices. We still want to invert them, but now we work up to scalar. So inversion up to scaling, you can think as taking minors of size n minus 1. Up to sign, this works, right? Everyone with me with spell 1? Now, is it the end of the fairy tale? I mean, is this map well defined? Certainly this cannot be a problem. I promised you there is something that now got through an obstacle. How do you think? Is this map from projective spaces inverting diagonal matrices well defined? No, I see people saying no. Yes, and then there are higher codimension problems. You can have 2 or more zeros on the diagonal, and your map taking n minus 1 minors will not work. Okay, so now we take a more powerful spell. It's called a blow-up spell. And I actually want to tell you how this spell works. So many of you know it, but so in general, to apply a spell, I will take a projective variety, and I will take homogeneous polynomials of the same degree. Okay, of degree d. And the spell is applied to such a variety so that not all of those polynomials vanish on X. Okay, and it goes like this. So we build a map to a projective space using our polynomials. This map will not be defined on points where all of the polynomials vanish. And we take a graph of this map. Graph, as you know from primary school. So we remember a point on which the map is defined. We remember its image. We take all such pairs and we close it up. Okay? Is it clear what's a blow up for everyone? Okay. But magic comes at a price. Namely, this thing, although it has nice map to X and PM, it can be very singular. And you may think, how is it possible? Maybe you learned in your studies that blowing up makes the singularities nicer and blowing up is always smooth. Well, it is true when you are blowing up smooth subvarieties. And the problem here is that that when we start with our map, it's also of this type. Inversion is given by homogeneous polynomials, degree n-1 minors. If you want, you can think what they are really on diagonal matrices. I don't want to say it aloud because this may create false impressions. But this blow up in n-1 minors that lives here could be very singular because as it comes, when you take matrices of rank at most R, very often this is singular. Yeah, so we take diagonal matrices of rank at most n-1. I claim this is a singular locus and this is a more general phenomena. And this is a question to the audience. If I give you some set of matrices of rank at most R, what's your first instinct? What's the singular locus? Rank R. But I take rank at most R. Yeah? Anyone wants to take a guess? Rank R minus 1. Okay. Okay. But there is good news. The wizard, from his ancient master, learned more about the second spell, about the projectivization, about the blow-up spell. And the ancient master used spell 2 exactly to make the situation nicer. That is, if you have something singular, you can apply your blow-up spell to the singular locus and hope that you will get something smooth. Okay, so what will we be doing? We have n-1 by n-1 minors. Well, they will be singular among n-2 matrices. So co-rank 2 matrices. So this is defined by n-2 times n-2 minors. Well, is this smooth? What do you think? No, because this R can change. So matrices of rank at most n-2 will be singular among matrices of rank n-3. And so on and so on. But there is a stop to this. Matrices of rank 1, they are smooth. And it turns out that we can use this spell all at once. So we have our inversion matrix, our inversion map, that we think as taking n-1 by n-1 minors. But then we take n-2 by n-2 minors. Then we take n-3 by n-3 minors up to 2 by 2 minors. Yeah. So Cj is here C to n choose j. Yeah, it's the ambient space for j by j minors of a diagonal matrix. And this is responsible for, if you take a graph, for blowing up rank 1. All two together are responsible for blowing rank 1, then rank 2. And if you take all of this together, you have blown up rank 1, rank 2, rank 3. Everything becomes smooth. And the graph of this map, in fact, will be smooth. Questions?
Taking principal minors?
Yeah, so these are diagonal matrices currently, but I will not take principal minors For diagonal matrices, I could, but I want to take all mine. Okay. So you may think that the quest is complete. We have realized a variety that somehow is smooth and dominates this diagram. And so the wizard could call it the variety of complete diagonal forms. But in fact, this is not the correct name. Anyone knows the correct name?
It's the torque variety of the Permutohedral.
Exactly. It's the Permutohedral variety. Okay, very good. Now, the construction already tells us that there are two types of distinguished divisors on it. That divisors meaning codimension one subvarieties, namely, our variety lives in a product of all of those projective spaces. So you can take a hyperplane in one of those spaces. Yeah, that's a codimension one thing. And you can pull it back. And I will denote this divisor by Li. Is it clear what happens? My permutahedron Pn lives in a product of n-1 projective spaces. And I can just take a general hyperplane cut in one of them, and I can see what do I get. I will get something of codimension one in Pn, and I want to call it Li. I think in Andrews Burgett's papers, it's often gamma I. In Juni's paper, L1 and Ln-1 are often alpha and beta. Okay, questions? No questions? Okay, but the procedure of blow-up has one more feature. Namely, if you think about rank I matrices, well, this is certainly not a divisor. But after you blow it up, after you will take this graph given by I+1 minors, it will become a divisor known as the exceptional divisor. So our variety Pn comes also with another set of divisors, exceptional divisors, and you can think about this as rank I matrices, apart from the fact that now in the permutohedral variety, they are really a divisor, codimension one. Okay, so now there is reducibility versus irreducibility thing that I don't want to enter into. So in particular, what are rank one matrices? What are rank one diagonal matrices up to scaling? One can say rank one diagonal matrices up to scaling. Points, right? I mean, it's like 1, 0, 0, 0, 0. So if you blow them up, every point will become a divisor, but I really want to keep all of them, some of them, okay? Okay, very good. Yes. So this is still not the end, although the quest was completed, of the story about the wizard. So the wizard observed that you can do similar story when you take a projectivization of a linear space of diagonal matrices. Here in this conference, we think about this linear space as representing some matroid M, and you can take something which is called a strict transform, which essentially is like pre-image, but on full rank matrices, and then taking the closure. And you could start doing intersection theory on the permutohedral variety by intersecting this strict transform a few times with L1 and a few times with Ln-1. Okay, and what you get are absolute values of coefficients of reduced chromatic polynomial of a matroid. So let's check if we are on the same page. What if I would take this to be a permutohedral variety? So I just intersect L1 and Ln-1. This would better be some God-given thing, if these things are supposed to be natural. So anyone in the audience, what would happen when I intersect a few times L1 and Ln minus 1?
Binomial coefficients.
These are just binomial coefficients. Very good. I hope I'm not off with indices. Okay. You can go slightly farther, namely, you could look at intersecting any divisors Li to some powers. And the way up, so I should say this integral sign, this just means here count points. Yeah, so intersect and count how many points you have. Okay, this is the degree map. So this, if you are seeing this for the first time, you might have a guess what's a generalization of binomial coefficients. Now when you have like L1 to A1 times Ln minus 1 to Ln minus 1. Anyone wants to make an educated guess? Don't worry, it will be wrong.
You want us to say multinomial coefficient?
Yeah, but not. So these are mixed Eulerian numbers. And they are mixed volumes of hypersimplices. If you think how your permutohedron projects to the ith factor here, these are I by I minors of diagonal matrices. So the exponents give you the convex hull of a ith hypersimplex. So when you will be cutting with hyperplanes, you will be computing mixed volumes of those. Of course, you can put here xm and then get nice invariants of Matroid, known as Matroidal mixed Eulerian numbers. I think this name was introduced by Katz and Kotler, but before even that, they were studied by Andrew Berget, Chris Eyre, Spink, Tseng, and in this setting, certainly Postnikov of Kruatoru. So, okay, important numbers. Yes. So now let's shift gears. There is a science called quantum physics, right? And I don't know it. I know some people who know it, and I thought that the best way to learn a new thing is to start with axioms. And quantum mechanics actually has axioms. And I wrote a few of them. So axioms of quantum mechanics. So a system, whatever you think of, you, me, whole universe, is completely determined by a vector in a Hilbert space. Okay? Every physical property is a linear Hermitian operator on that vector space. And a measurement is a projection to eigenspace of the associated operator. The eigenvalues is actually what you read off from the experiment. And where you project, you know, your vector does not have to be a basis vector in the eigenvectors. So where you project, this is actually the quantum uncertainty, and the probabilities are more or less proportional to modules of the coefficients of your vector. Okay? I'm not joking. These are really axioms of quantum mechanics. Okay? They more or less tell you that this is a subfield of linear algebra. These are not all axioms, but first three. Now, when you do quantum mechanics, there's an important thing to understand. Like if you take a linear combination of E1 and E2, well, as mathematicians, we know this does not mean that with some probability it's a vector E1, and with some probability it's a vector E2, right? It's really a linear combination of the two vectors. Yeah? And in physics, we really have to distinguish the two things. Yeah, one is superposition, which is a linear combination of those eigenvectors. And one is a situation when our system is actually in one of the states, like E1 or E2, but we don't know in which one, and we only know probabilities. Maybe it's in E1 with certain probability, maybe it's in E2 with certain probability. Now, if every vector was an eigenvector, maybe it would have been a good idea to remember our uncertainty just by taking linear combinations of E1 and E2. But now, when we have axioms of quantum physics, we know this is a very bad idea because we would mix a superposition, really a vector, that is a linear combination of two eigenvectors. We would mix it with our lack of knowledge, whether we are E1 or E2. And the physicists have overcome this by, instead of remembering the vector, remembering a rank 1 symmetric matrix associated to it. They I think sometimes write it like that. But this is nothing else than the Veronese. Yeah, you know how to cook up a symmetric matrix from a vector. Yeah, rank 1 symmetric matrix from a vector. And now you can do two things. You can take linear combinations of eigen vectors, getting really a vector and then getting a rank 1 symmetric matrix after this operation, or you can start mixing your rank 1 matrices, getting a higher rank symmetric matrix. Okay?
Point. Quantum mechanics is a Hermitian matrices, yeah? Or,
yes, yes.
But
so I sometimes say symmetric, sometimes Hermitian, depending whether I think real or complex. Okay. I prefer symmetric, and somehow for later motivation of the talk, symmetric will be better. But every a lot of things are Hermitian. Operators are Hermitian. Okay. Yes. So you know, of course, like a linear combination of VIs and doing this is a different thing than a linear combination of those rank 1 matrices. And yeah, this is like superposition, and the linear combination of those rank 1 matrices is our lack of knowledge in which state we actually are. And this matrix that is obtained by linear combinations of our lack of knowledge for experimentalists is as good as knowing the state, because you can read off from it all probabilities, what will happen after you do expected values of all of the probabilities, of all of the measurements you can make and in which state. Okay, so let's sum it up. If we are in classical physics and every vector is an eigenvector, this procedure doesn't really make sense because we are just putting 1 on a coordinate. And then linear combinations of diagonal matrices versus linear combinations of vectors, it's the same thing. You would never leave that. But once we really go to symmetric matrices, it makes a big difference. And as far as I understand, this is when physicists really say that there is a quantum phenomena. When your matrix is not diagonal, but it has off-diagonal entries. Okay? Okay. Okay, so there is physics and there is quantum physics. Now, there is a topic I cannot tell you about, which is very similar in analogy. There are polytopes and there are spectrahedra. If you think about polytopes as a linear cut of a positive orthant, then a spectrahedra is a linear cut of positive definite matrices. And here I advise everyone to talk to Mario Kumar, who is an expert on the topic. Okay, so if there is physics and there is quantum physics, if there are polytopes and there are spectrahedra, this means that our wizard should also have an analogy. Okay? And we want to know what's here. Yeah, is motivation clear? Okay. So what's the analogy of the wizard? So I hope the left thing everyone remembers from the fairy tale. We have a projectivization of diagonal matrices. Yeah, what is this map? What is this map? Anyone remembers a fairy tale?
Projection.
Yeah, that's a projection if you think about it this way. If you think about it this way, it's blow up of.
Lower rank matrix.
Perfect, that's the correct answer, yeah? Not points, lines, yeah? Low rank matrices. Okay, and this was contained in this projective space. Now, if you think about those analogies, they always say that, well, diagonal matrices are special cases of symmetric matrices. So we should have an inclusion of n by n diagonal matrices in n by n symmetric matrices. So this is my notation for n by n symmetric matrices. Okay? What will be this map? Anyone wants to have a guess?
Well, given the analogy, presumably CQM is you take the product of k by k minors for all k.
Exactly. So here we will take projective spaces that are ambient spaces for all k by k minors of my symmetric matrix, which we can also say that this is like a blow up of rank 1, rank 2, and so on. Okay, so this variety actually has a name, and if you feel now the quest is even more complete, you can call it the variety of complete quadrics. Okay, because quadrics are like symmetric matrices. And you can go even farther to n by n matrices, and you can blow up rank 1, rank 2, and you get a variety of complete combinations. Yeah, I have listed a lot of co-authors. I should say this is very classical. I mean, those varieties appeared in the literature before I was born. Okay, it's a very nice exercise to think where k by k minors of symmetric matrix live. It will make you better understand Plucker relations. Yes?
So isn't CCM also GN2N and CQM is Lagrangian Grassmannian?
Wow. No.
I'm cheating.
But almost.
Okay.
That's amazing. If I heard it once I saw this story, that would save me probably half a year of my work. But
Okay, but I do want to know why I'm wrong then at some point.
it's a Chow quotient of those that you said by a sister action.
Oh, okay.
So the Lagrangian Grassmannian and the Grassmannian are the analog of the cube for Pn. That's very much towards generalized Schubert varieties. Because matroidal Schubert varieties, they don't live in Pn, they live in P1 to the n. That's a great question. I wish I had more time to talk about this. Okay, so what happens? Because this is so analogous, we still get divisors Li and Si. So Li, well, depends where we look at it, but it always comes from a hyperplane cut for I by I minors. And the pullback of Li is Li, nothing changes. We still get exceptional divisors. And well, you know, rank K symmetric matrix that happens to be diagonal is a diagonal rank K matrix. So this picture really behaves nice with respect to those divisors. But now we could do slightly more. We can take a linear space of symmetric matrices, and we can associate with a strict transform in complete quadrics just by taking invertible symmetric matrices, yeah, taking prim each of those. Yeah, these are blow-ups, so they are birational, close it up, and you get XL. Well, and in analogy to the wizard story, we can study the numbers by intersecting with LIs. Yeah, we can be very proud of ourselves that we devised new invariants. Well, the problem is that some of them were known like 200 years ago. And the maybe first person to study them was actually Schubert, who realized that if you take XL equal to CQ, this number actually counts the number of quadrics, so 0 locus of degree 2 polynomials that pass through A1 general points, A2 general lines, its tangent, A3 general planes, tangent to general, and so on and so on. So his motivation was reversed. he wanted to know how many smooth quadrics pass through a given number of points, is tangent to a given number of lines, is tangent to a given number of planes, and and he devised a lot of this setting, maybe not all, to turn it into an intersection problem. But currently it's just a translation. I mean, you know, intersection problems, they can be as hard as it gets. He called those numbers, I think, characteristic numbers. So these are Schubert's characteristic numbers. Well, if your L happens to be contained in diagonal matrices, you really recover the story of matroidal mixed Eulerian numbers. There is also sync here, this polytope versus spectrahedron. You get something that is called algebraic degree of semi-definite programming, studied by Randstadt, me, Sturmfels. And one of my favorite motivations is from statistics. This is actually part of the work with Rodica, Carlos, Martin, and team, and Leonid. You get degree of Gaussian linear concentration models. So if you know ML degree of toric models, it's not that. It's a different ML degree of multivariate Gaussian models. But well, if you want to know the degree of these models, it's related to ML degree and those numbers. So I think my hope is that I persuaded you that we might be on the right track, because we have some setting that that generalizes quite a few numbers. The bad news is that I decided not to talk about those things. Every single I mean, this could be a talk, but recently we managed to go in the opposite direction. So quite a lot of my work was trying to see what the wizard did, or what some of you here did, and try to adapt it to this setting. Log concavity, for example, goes through nicely. So if you will build a polynomial, we will talk out of it, you will get a volume polynomial, it will be Lorentzian, you will get a lot of log concavity results. But to be honest, I think in statistics, people rarely conjectured log concavity. They mostly conjectured explicit formula. So we used it as a tool to obtain formulas. But only recently, I think it's the first time, where we actually managed to go back here. So to use some ideas that were on the right and go back to combinatorics. And you will be the judges if this is interesting or not. Okay, so well, if we want to use something on the right, and you know, in combinatorics you have a lot of tools that still we don't have on the right. We better steal from someone very powerful, and maybe the person very powerful will be Schubert. So how did Schubert manage to actually do something with such intersections? Well, he had a very good idea that works in large part of mathematics of breaking one problem into a few easier problems, and it goes like this. So I told you there are two types of divisors, Li and Si. In none of the cases they generate the cohomology group. None of the three cases. In the middle and right case, they generate the rational Picard group. In the left case, they generate the Sn invariant part of the cohomology ring of the Permutohedral. Okay? But they are not linearly independent, Li's and Si's. And this is something that already Schubert observed. The relation is very, very simple. And when an index doesn't make sense, it means that I put 0. Okay? Out of curiosity, anyone knows this relation?
Simple root in fundamental weights.
Wow, it's amazing. Yeah. This is the relation between simple roots and fundamental. So sum of EIs and differences of two consecutive EIs in type A. So if you want a slightly challenging exercise, think where does type A root system come in here? Okay, but very simple relation. And you know, those LIs, they had a great geometric meaning. As I told you, the condition Li means being tangent to an I-dimensional general linear subspace. Now the SIs seem not to have a very good geometric image. So at first you may think that Schubert went crazy, replacing Li by linear combination of the SIs, which is possible because both Li and Si, they rationally span the Picard group. But it turned out to be really good because there is a recursive model for the divisor Si. It breaks the problem when you are intersecting Li's on Si into two smaller pieces. And I only want to give you what does it mean in combinatorics. And it's a fact that you know. In combinatorics, the corresponding fact is that facets of the permutohedron can be represented as products of smaller permutohedra. Okay, so if you will be intersecting with a facet, you suddenly reduce your problem into two smaller problems. And in combinatorics, people also use that. In Schubert's case, it was slightly more complicated. You had to do a relative construction of the smaller problems, but still he managed to do it. Okay, so what's the conclusion of this? It's good sometimes to trade LIs for SIs. And I will give you one instance of it. Okay, so I told you about matroidal mixed Eulerian numbers. I told you about mixed Eulerian numbers. It's time to talk about Eulerian numbers. Anyone knows Eulerian numbers? Some people know. Yes. So Eulerian numbers are very old. The relation to what we are doing is what happens when you just keep one Li on the permutohedron and intersect it with itself. So in other words, what's the volume of a hypersimplex? And if you were here for Professor Spack's lecture, there is a combinatorial interpretation for Eulerian numbers. Anyone knows it? What's the NK Eulerian number? It counts the number of permutations of n elements with exactly k ascents. And an ascent is like when the next number is bigger than the previous one. Okay, so this is something that Professor Pack would say it's good because it's in sharp P. But if you go to Wikipedia and ask for the formula for Eulerian numbers, this is not what Wikipedia will give you. Wikipedia will tell you something else. It will tell you that the n-case Eulerian number is sum from I equals 0 to k minus 1 to the I, n plus 1 choose I, k plus 1 minus I to the n. Okay, now, who in the audience would call this an explicit formula? Okay, let's say slightly more than half. Who would call it problematic? There are some repetitions. Okay. Can you see what's the problem? This formula doesn't even tell you that this number is positive. Okay? But I would call it a closed formula, and I think Wikipedia does call it a closed formula. Okay, so now I wanted to read you a citation. There was no place to put it on a board. So it's a citation from PhD about mixed Eulerian numbers. Okay, well, it was somewhere here. Okay, well, anyway, maybe I will just say what I remember it. It says that a formula, a closed formula for mixed Eulerian numbers should not be expected because we don't even know what happens when we allow just two LIs. So this is when we allow just one LI, but if we allow two, that's already not known, and you should not expect a formula for the general case. Now, there are recursive formulas. There are formulas in special cases, but so this you should think as k to top power. Okay. Yes. So what's the trick? Well, the trick is try to understand all of them. And for those of you who like Lorentzian and volume polynomials, I think this will be very natural. We define a polynomial that counts the intersection of such divisors. So what are the coefficients? Well, the coefficient of xa is n minus 1 to the a, L to the a. I'm using the multi-index notation. Okay, maybe I should put an integral here, but I hope it's clear. So understanding this polynomial is completely equivalent to understanding all mixed Eulerian numbers. We agree? I mean, multinomial coefficient does not matter that much. Okay, so if we understand this, we understand this. Now, there is a related polynomial that we could define. Namely, I could see what happens when we intersect, oh, that would be exactly the same. When we intersect the SIs. Okay? Now, this formula, well, you can see it as a matrix, exactly tells you that this polynomial is this polynomial up to easy change of coordinates. Linear change of coordinates of polynomials that we learn at school. Okay? Really, nothing more. Yeah, just plug in. Okay? Okay, so up to linear change of coordinates, these two are equally hard. So you have to make a choice. Either you believe that linear changes of coordinates are hard. And it could be because of things like that. Or you have to accept that these two polynomials, they don't really differ much. Because one is a linear change of the other. Okay, so now time for some good news. If you take S B1 C1 times S B K CK, and you assume that B1 is smaller than K. So I really take any intersection of any of the exceptional divisors. This is -1 to n minus k minus 1. Now comes a multinomial coefficient n b1, b2 minus b1, b3 minus b2. Oh, I see I didn't plan it well. N minus bk. And now comes a product of binomial coefficients. I will write it here. So notice that now there is really no turning back. You have to call this last thing a formula. And the reason is that even saying that you're unhappy about the sign will not work because you know the sign. The only thing that determines the sign is here. Okay? So intersecting exceptional divisors is really, really easy. Okay.
This is an Euler characteristic.
Sorry?
This is an Euler characteristic at the end of something. Because this corresponds to, you know, simple roots, it's like weights of the tangent bundle, and it's like a top gen class.
Okay, here I would have to think, but certainly if I just intersect L1 and Ln minus 1, this is the Euler characteristic of the complement of the determinant of symmetric matrices cut with the correct numbers of hyperplanes. For this one, I would have to think. Okay, so if you do intersection of L1 and Ln minus 1, this number will give you Euler characteristic of determinantal hypersurface, or more formally, it's complement and cut out with hyperplanes.
On the Permutohedral.
No, on CQ also. So if you want to take the determinant of symmetric, well, that depends what you want. If you want to take determinant of symmetric matrices, or if you want to take determinant of n by n matrices. Yeah. So Juni has a paper with that essentially works for gradients of any polynomials. So in particular, it has to work with gradients of determinants. Okay. Yes. So I still have 5 minutes for fun. That's actually nice. So I want to tell you something. We had this intersection of L1 and Ln minus 1 on the Permutohedron. And we know that we got binomial coefficients. And if we put all of them together, we get Pascal triangle, right? And if you read it row-wise, the coefficients are log concave, right? But Pascal triangle has more fun to it. Yeah? You could try to read it column-wise, right? Well, column-wise, it's infinite, but it is a polynomial. Yeah? So you should think about Pascal triangle as like Ln minus 1 to n minus 1 minus a. Okay? And this seems crazy to read it column-wise, because this Permutohedron a priori has nothing to do with the next Permutohedron. Yeah, but still, n choose k is a polynomial in n. Okay, so I'm trying to persuade you that there is a natural question coming here. Question is, what's under this board? How would you build the Pascal triangle?
Like an inductive limit of Permutohedral varieties.
Yeah, so there is a whole branch of infinite dimensional algebraic geometry, and it's absolutely great. And probably there should be some connection, but I would like to first go to quantum. What is a quantum Pascal triangle?
You analog?
I didn't
So it's like Q analog?
It's more like CQN.
CQ analog, yeah. So you know, this I can not only write on the left, I can also write it in the middle, and on the right, I just have to adjust the exponents so that the dimension matches up. Okay, so this is the quantum Pascal triangle. You see, it's still I didn't end. I mean, it has to be symmetric, like Pascal triangle. It's no longer a triangle because the dimension of symmetric matrices does not grow linearly. And the rule to obtain it is slightly more complicated. Here is 1, 1, 1, 1, 1. Here is 1, 2, 3, 4. Here is 1, 4, 9, 16. You can probably still guess a formula. Farther is harder. I think the world record used to be by Stockrat, Chardin, Eisenbach, and Ulrich, who gave a formula for 1, 2, 3, 4, fifth row. Okay, so some of those numbers you can find in 19th century literature because this is the number of quadrics that pass through 1, 2, 3 points and are tangent to the correct number of general hyperplanes. But there are a lot of properties shared with usual Pascal triangle, and a conjecture coming from statistics by Sturmfels and Euler that we proved is that actually every column is a polynomial. Okay, so that this actually makes sense. Okay, and indeed, from the point of view of algebraic geometry, this should be completely crazy because these complete quadrics have nothing to do with next complete quadrics and next complete quadrics and next complete quadrics. And these polynomials, we have now recursive formulas. I mean, I can later show you how the 17th one look like. It's pretty long. It takes like 1/4 of the page. But they always have this nice property that the coefficients are alternating and seems to be related to log concavity. And I call it mysterious log concavity. So question, can you prove? Of coefficients of phi k. So this is phi n4.
But only log concavity, not ultra log concavity.
I don't know. I mean, you know, it's all conjecture and it's of very different flavor than just the counting of points. I mean, it could be just all false. So we can say that maybe is it true? Not can you prove? But as already the audience started to suggest, maybe, and then this will be on a crazy stretch dreaming level. Maybe there is some Hodge infinite dimensional geometry, because if you would like to govern all CQs, you probably would like to have something infinite dimensional, but I don't have any evidences that such a thing could or should exist. Okay, so just last minute to sum up, those results that I presented, I just took the theorem from the forthcoming paper and tried to find the easiest version and apply it to uniform matroids. So we have versions for matroidal mixed Eulerian numbers and formulas like this. They are all based on the same idea, that if you put xm here, it's much easier to intersect with the exceptional divisors than with the LIs. And there is one more result I wanted to share with you. Now, if you know the cohomology of Permutohedron, you know probably that it has more divisors. The divisors actually correspond to proper subsets of the ground set of n elements. And one could wonder, why are we intersecting with the LIs? I mean, there could be many other invariants coming by intersecting with other divisors. Yeah, if you are blowing up points, you could intersect with the exceptional divisor that is a sum of all the divisors from points, but you could also intersect with the exceptional divisor coming from this point. and you should get more invariants. Well, the problem is that most of those things will be not invariants of matroids, because you can permute your ground set and your divisor will change. But when you are permuting, you formally get a different matroid, but you get an isomorphic matroid. That is when you really want to get information about invariants of a matroid. I believe, so my original motivation was that LIs are very general here. So let's just intersect here. But I believe that these are the natural objects that you get from intersection theory, not the whole intersection theory with the cohomology ring of the Permutohedral, but rather the SN invariant part to capture invariants of matroids. And the good news is that these are all valuative invariants. That is, we proved that intersecting with LIs for loopless matroids is exactly the information in a so-called Dirksen's G invariant, which was proved to be a universal valuative invariant. Thank you very much.
Questions for Mateusz?
So like these numbers are combinatorial, what do they count?
They count, well, not combinatorial in the sense of Professor Pak. So they count the number of smooth quadrics in a given dimension that pass through a given number of general points and are tangent to a given number of general hyperplanes. So which row, that's the dimension. How much from the left, it's the number of general points. How much from the right is the number of general hyperplanes. And then this needs to meet, because otherwise you would say 0 or infinity. So somehow the number of points and the dimension determines the number of hyperplanes.
You don't have anything like the number of k-element subsets of it.
No.
So you conjecture low concavity in both directions, like vertically and...
No. So this one, Juni proved.
Yeah. Okay.
This one, yeah. This one for me is more mysterious.
There's no spell for that.
Maybe there will be, but we have to work on it.
You mentioned Anabelian Matroids in your title. Can you say what where the Anabelian Matroids?
Yes, that's a great question. So Anabelian Matroids don't yet exist. Representation of a representable Anabelian Matroid will be a linear space of matrices, and the corresponding class will be the class in CCN or CC or CQN via strict transform. But I can tell you how to find the definition of an Anabelian matroid. Yeah? Pick a paper of some great people in combinatorics and take as many adjectives as you can that classes of matroids satisfy. That's step one. Step two, add some numerical data. Like, for example, the class intersected with L1 is 1. Yeah? So everything that the class of a matroid in the cohomology ring of the Permutohedral satisfies. 3, check that what you picked is beautiful and you're amazed by it. And if the answer is yes, that's the definition of Anabelian matroid. If the answer is no, go to step 1.
If I look at either the subring of the Chow ring of a matroid generated by the hypersuffix classes by the Li, or I look at the point graduality quotient, does that have the KO package, full KO package?
The subring generated by the Li. Wait, isn't this like this cohomology of Peterson variety?
Per a wonderful variety, not per median. Like I'm saying, so if you're living in complete quadrics, you only have
are you asking here? Here I can tell you everything.
Yeah.
It breaks everything. So the subring in the cohomology generated in degree 1 it's not symmetric.
But like, even if I go to the wonderful variety, you know, you were saying like, oh, these other non-symmetric divisors, they suck, but you need them in order to get.
But the non-symmetric divisors only exist here. They do not exist here.
Yeah.
Here it's the whole Picard group.
Yeah.
It's the cohomology ring is not generated in degree 1, but on Picard group I get everything.
Yeah.
You mean that here, if I pass to then as an invariant part, many properties of the ring can break.
Well, I'm asking, I don't know.
But at least like the volume level still will be the volume of polytopes of this subring, so you will have some properties like Hodge-Riemann.
Yeah, so you get Hodge-Riemann degree 1 for free.
If you take the invariant subring, you're just taking the cohomology ring of the quotient.
Yeah, so I'm
Q manifold.
I'm asking if you go to a wonderful variety, which doesn't have the SN action anymore.
Okay.
But wonderful variety, you mean like after you fix a matroid? Or?
Yes.
Yeah, so I rarely go there. I prefer to think about this class of a matroid as a class in the Permutohedral where there is an SN action. Okay, no, I haven't studied after you quotient by the annihilator what happens. Sorry.
Question, Arya.
Yeah, let me reformulate my question from before. So do you have an example of such a column polynomial where the coefficients are not ultra-log concave?
I haven't checked.
Okay.
We can
And
check.
you also haven't checked for real rootedness?
I think real rootedness. I have to be consequent. What we checked, we certainly checked up to 50, or at least my students say they checked up to 50 log concavity. Now, whether we checked real root, one of the nice properties was failure. This I remember. Sorry?
If I remember correctly, real root.
Okay. Leonid says we checked that it fails to be real root.
Okay, an ultra-log concave?
This we did check.
Yeah, but one question. So what do you mean by ultra-low concavity? It's an infinite sequence of numbers.
But it is a polynomial. That's the theory.
But you don't want the actual numbers, but so
The coefficients of the polynomial. So it's really like very strange. I mean, you have just numbers that count something, and column-wise, there turn out to be a polynomial.
Yeah.
There is a factor that I understand.
Yeah.
There should be zeros at the beginning. And then there is a strange factor I completely don't understand, but seems to have nice coefficients.
So you don't care about like the low concavity of the actual column, but rather the coefficients?
Yes,
The
yes.
interpolating polynomial.
Well, column is just evaluation of this polynomial. So well, it is what it is. So somehow I feel understanding the polynomial is understanding the column.
So let's thank Mateusz again.